All right. So covalent bonds. When atoms share electrons. These are examples of covalent bonds. We'll start with the one at the top. If you look at the top, this is hydrogen. Hydrogen only has, well, first of all, it has an atomic number of 1. That means it only has 1 proton in the nucleus. We can assume that it also has 1 electron. And it does, right? So it's 1 proton, 1 electron going around it. So it's like a planet with a single moon orbiting around. But that first orbit could hold up to 2. It could. It's only got 1 in it, but it could hold up to 2. And, you know, these atoms really like to try to fill up their orbits or their shells. They want to get the maximum number of electrons in it. They're insecure atoms. So hydrogen would like to have a second one. It's never going to happen for it. But if it borrows or if it shares with another hydrogen, it could. It's like you going in with like a family member to purchase like a really nice car that you couldn't afford on your own. And you each, you know, she works at night and you work in the day, so you can take turns driving it. And you can like be important for that time that you drive it, but with half the price. Atoms do this all the time. They share their electrons. So it's kind of like, it's like this electron, this electron here is going around this atom, and then it's going around the other one. It's doing like imagine it doing like a figure 8. Same thing with this electron. It's doing a figure 8 around both hydrogens. So they're both going around each other so fast, like they're really fast. They're so fast we you know, when they look at these things, they don't actually see them. They just see these clouds that they make as they go by. So we don't even know how fast. But they're going around each other so fast that it holds them together. So it's a relationship based on sharing. And you notice that it just says H, and it doesn't have, we didn't put like P, 1P inside. We didn't like write all that stuff. But you know that hydrogen, the atomic number of hydrogen is 1. So anyway, that's not the important thing. The important thing is that they're sharing electrons. And this is a shorthand for it. H-H. The dash means that they're sharing, you know, it's a covalent bond. The dash means a covalent bond. Which I'm going to start using probably starting today. So I don't want to keep writing all those atoms. And this is even a shorter way. So here they wrote H2. But they didn't tell you anything. It's just saying 2 hydrogens. Right? But so if nobody says anything to you, you just assume covalent bond. Right? That's like your default bond. For example, like for water, you know, they write H2O. Well, are those ionic bonds, hydrogens? No, covalent. They're just regular covalent bonds unless they, you know, if it was an ionic bond, they would have pluses and negatives. And same thing here, CH4. That just means 1 carbon, 4 hydrogens. And that's all it says. That just means that they're doing covalent bonds. Most atoms bond by covalent bonding. So they want to fill their valence shell. If you remember the valence shell The valence shell is whatever the most outer shell is. So co meaning like sharing, like cohabitate. They're covalent. They're covalent. They're sharing their electrons. If you notice here, this is an oxygen, and then it's like an equal sign with another oxygen. So that means that they're sharing 2 electrons with each other. So there's some rules about this. They're not very hard because we're only dealing with the 4 atoms that we talked about, right? The 4 atoms that we've been talking about are carbon, nitrogen, oxygen, and hydrogen. Those are the 4 atoms that I was pushing in the first class. So if we look at those, we have hydrogen. Hydrogen has 1 electron in this shell. And I'll rewrite it here. Here's like a hydrogen, 1 proton. Here's the electron going around it. How many can that hold? It's got 1 inside of it now. How many can I put in there maximum? Yeah, another 1, right? And so there's rules about when you share with somebody, when atoms share with each other, there's like rules. And the first rule is you can't get more electrons than are going to fit in here anyway. So you only get, when you're sharing, it's like you own it, even though you're sharing it with someone. But it's like the same effect. You own it. So you only can share, well, first of all, you only have 1 electron to share. So you're not going to share 1 electron and then some atom is going to share 4 electrons with you. That's not how sharing works. At least not for atoms. I give you 1, that means you're going to share 1 with me too. So I share 1 with you, that you share 1 with me. If I share 2 with you, you'll share 2 back with me. But they're always like equal. There's never like this sharing where you give a lot of electrons, but the other atom only gives like 1 or 2. But anyway, it doesn't matter because you can't fit more than 1 more electron anyway. So some other atom, let's say you have an atom of, I don't know, whatever, gold, and there's like a whole bunch of electrons, right? Gold's only going to share 1. That's all that's going to fit here. It doesn't matter how many electrons are available to share. There's only space for 1. And once this hydrogen shares the other one, they both feel like they're fulfilled, like they've got their valence shell maxed out. That's all they're interested in. Same thing here. If you look at oxygen, if I were to draw out oxygen, I'm going to put OXY in here in the nucleus. But we know that the atomic number of oxygen is what? Atomic number of oxygen. Between 1 and 10. Can't always be him. 8. 8. So I'm going to draw 8 electrons around here. So how many am I going to put on this first thing? There's 2. Now I know that they draw them different up here. And then I make my second one. And I put the other 6, right? How many can this hold, this outer one? It can hold up to 8. So I got spaces for 2 more. Right? That's why they're sharing 2. It's not about how many you got here to share. I mean, you gotta have enough to share, but it's about how many spaces do you have left. This one only has 2 spaces. So it's only going to get 2 electrons shared with it. The garage only holds 8 cars. You can't go in with somebody and get 3 more cars. You already got 6 cars in your garage. That's it. There's no more room. You get 2 more, you can max fit 8 in there. It was working in my head when I was thinking of the analogy. Most of my analogies are going to be like, what? That's fine. Just ignore it. But that's why it can share too. So hydrogen, there's like these, if we have these 4 atoms, hydrogen can share, can bond with one atom. I'm going to put bonds here. How many bonds can these atoms make with other atoms? Hydrogen 1. Hydrogen can only grab onto one thing. That's it. Whenever you see hydrogen here, you only see one dash coming out of it. So hydrogen's got like one arm. That's it. It can grab onto one thing with its one arm. Oxygen has 2 arms. It can make a choice. It could take both of his arms and grab onto different atoms. Look, that's what's happening here. This oxygen's grabbing onto this hydrogen and that hydrogen. Or it could take both of its arms and grab onto something else. I have a lot of stuff going on up here. We call this a double bond, by the way. When it like does 2, you're not going to see that very often. But that's a double covalent bond. That second one, oxygen, this is an example of a double covalent bond. This is a case where oxygen is grabbing onto 2 hydrogens. Nitrogen can make up to 3 bonds. Because now we got to think, okay, what's the atomic number of nitrogen? It is something. Atomic number of nitrogen? So I know I keep asking you on purpose. 7 protons, 7 neutrons, 1, 2, 3, 4, 5, 6. I gotta get rid of 1. There we go. So there's 5 electrons here. These 2 make 7, but we're really looking at this outer shell. There's 5 here. It could hold up to 3 more. So that's why I put 3. And lastly, if you look at the superstar of all these 4, it's going to be carbon. Carbon has an atomic number of 6, which means that there's only 4 electrons here. So it's got 4 that it could share with somebody, and it's got room to get 4. So carbon can make 4 bonds. You're always going to see 4 dashes coming out of carbon. You're always going to see 3 dashes coming out of nitrogen. You're always going to see 2 dashes. And if you look at these, that's what's happening. There's 4 dashes coming out of carbon. You're not going to see 3. They do the maximum, right? These atoms share the maximum that they can share all the time, at least in biology. Carbon's always going to share 4. Carbon's got 4 arms, and it will grab onto 4 things. It might take 2 of its arms and grab onto another carbon, but it's going to use all of its arms, right? It's going to use all of its bonds. It's got room to put 4 more electrons. It's going to put 4 more, whatever it can hold. Nitrogen's always going to have 3 things bonded to it. Oxygen 2 and hydrogen 1. So, like oxygen doesn't go partial. It's not going to grab onto something with 1 arm and just let the other arm dangle. These atoms are all in. So whenever you look at them, they look kind of weird now. And we're going to move away from this thing in the middle here. And we're going to move to this one on the right. This one here. And you're always going to see 1 dash associated with a hydrogen, and you're always going to see like 4 dashes associated with a carbon. But they're sharing, in all the cases, in all these cases, they're sharing electrons. So covalent bond share electrons. There's two types up here. There's a single, and we don't really call it single, we just don't say anything, right? But there's a double. The second one, the oxygen attached to the oxygen, that's a double covalent bond. You're only going to see that 3 times in this class. And probably mostly in biology. There's other examples, but mainly we see this 3 times. One time is here, an oxygen will do a double bond to another oxygen, and carbon will do the same thing. That's common, you'll see that. So sometimes carbon uses 2 of its 4 bonds to attach to another carbon. And by the way, the double's a little bit stronger, right? Because you're grabbing onto something with 2 arms instead of 1. So it's a little bit of a stronger bond. And then carbon will do it with an oxygen sometimes. And you'll see that too. Carbon and oxygen will grab onto each other with 2 bonds. Other than that, you're not going to really see any examples of it. There's a triple, I'm not going to write it, but there's a triple bond, like nitrogen. Nitrogen triple bonds with another nitrogen. Like this air around us that we're breathing in is more than 3/4 nitrogen. We're breathing in nitrogen, but we're breathing it back out. We can't break the bond. Neither can plants. Think about fertilizer. It's nitrogen. It's partly nitrogen. Like it's the most important one. But nitrogen's in the air all around us, but the plants cannot break that bond. Like they can't. And you know, like when like this is too big of a molecule for us to make it work. We can deal with one of these, but we can't deal with 2 attached together. So if we want to use it in our body, we have to break those 2 apart, and then we can use each one. Same thing with plants. Plants, it's too big. It doesn't fit into the places it's supposed to go. So the plant would want to break it apart, but it can't. So even though we need nitrogen for life, it's hard to break apart. So that's why we give fertilizer to plants. It's like synthetic nitrogen. And we get our nitrogen because, no, let me stop. So single bond, double bond. We're going to talk about in a minute a third kind of covalent bond, which is called a polar covalent bond. So let me remember where it comes on my slides. So you guys watching from home, and I'm going to record this, a lot of the stuff that I'm writing on the board, I haven't set up in the lecture. So what I did is I put the same rules that I was telling you. Like the first shell holds 2, second shell holds 8. You can only share what you're going to get. And then the bonds, you know, like carbon can make 4 bonds, nitrogen 3. I want you to know that. So there's 2 things you have to know with each of these atoms. 1, the atomic number. So you got to know the atomic number of carbon 6. But you got to know how many bonds can carbon make? Like how many different atoms can it grab onto? 4. All right, yeah. The next slide is going to talk about polar covalent bonds. Does anyone have any questions so far? This will be not only in today's video, but I made like a separate video that talks about this, which I will I'll also post. So you're going to see like maybe 3 videos today, like 2 more that are just about They're kind of, if you watched one of the two that I had already posted, it's kind of like that, right? And then the lecture from the class. So don't get overwhelmed by the videos. You might see like 6 videos or something like that for like material that's going to be on the quiz. But it's redundant, right? Some of it, the lectures, the stuff in the classroom lecture is covered by the videos, right? So it's not actually 6 videos. There's 3 reasons why you might be silent and not asking questions. The first reason, of course, is the best one. The first reason is that you get it all. You understand it, or you learned it in high school, but you already know it. That's a great reason. The second reason is that, look, you're bored. You don't feel like talking this morning, and you're not used to talking in class, and you're just waiting until I stop talking and you can get up and go. That's my MO. When I'm sitting where you're sitting, I'd be on my phone. I'd be on my phone, even though I know that the person standing here where I'm standing can tell that you're on your phone, even though it's like under your desk or behind your book. But I'll do it anyway. I just can't help it. And then what I should be doing is like writing shit down, but I don't know why. And then I think, oh, I'm going to watch the video later, which is like a joke for me because it just never happens. And it just like sits on my head. It's like, hey, you got a quiz Wednesday. My kid's the same way. He's just about to graduate. It's the same way. Got a quiz Wednesday. And then it's like Tuesday night. It's still not done. And then you go open it up like at midnight and you're just tired. And you're like, I'm just going to sleep. We'll look at it in the morning. And what ends up happening, I see y'all in your cars in the parking lot. It's too late. It's not going to happen. It might happen if you take some other class, but it's too late to flip through your phone like that. You can't get all that stuff in your head. It's like, it's too difficult. That's the second reason that you're bored. Third reason is that you're completely lost, right? And you give up. You're like, fuck it. I don't understand any of this. But you don't want to say anything because we've got like this thing in the classroom that you keep your mouth shut so that I will finish talking and you can get up and leave. Like, I've got a fixed time in my head. It's about 11 o'clock. I got a fixed time and I'm going to keep you until that time. So speaking all class or not speaking doesn't get you in your car any sooner. What it does do is that it ties me up and it slows me down, which is what you want. You don't want me to keep going and going. So if you're lost on something and you're like, back way the hell up, like way up. Yeah, I will. And you slowed me down. So I can't put as much stuff on the test. You actually do favor to your class. But we always tend to get pissed at people. I do. Gosh, that's another question. Shut up. But really, I should be saying yes. I got to think of some questions too. I got to slow this dude up. That's just keeping him from going. Because I won't give you stuff on the test that I don't talk about in class. Anyway, my point is, you're completely lost. Now, the second class, that's the time to slow me down. These are like fundamentals. You're seeing it, some of you are seeing it as something you just have to get through until we start getting to biology. But it's not like that. Like if you were taking psychology and you're totally bored with like a chapter, whatever, I'll just get through that. And then when she gets to the next chapter, I'll start paying attention. This is different. This all like builds on itself. So if you're lost now already, you have no idea when I say the word proton, you have no idea what I'm saying. It's not going to help you later because it's all like built. So do you know what protons are? What charge they have? All the board. If you're stuck, you don't know what I'm saying, stop me. You are not going to, you're only helping the class, not hurting them. It's less on the test, and I'm not going to let you out any sooner or later. So, Ionic covalent bonds share electrons, and they share electrons because they want their shell, valence shell, right? That outer shell. They want it to be filled up. That's why they do it. Ionic bonds, positive and a negative, sticking together. So if you think about which bond's stronger, you have one bond where you have like theft. Like one atom stole an electron from the other one, and then they got together. It's not a relationship that's strong. It's based on theft and possibly coercion and enabling. That's not a relationship that's going to last very long. It's going to end up on 2020 or Dateline NBC or something like that. That's really what's going to happen. Covalent bonds, it's a relationship based on sharing. That's stronger. This is a messed up relationship. This is a covalent bond also, but it's a polar covalent bond. So this is water. How do we know it's, well, we know because it says right here H2O, right? H2, two H's, O. So it's like H2O1. Whenever it's a O1, they don't put 1. So they're just telling you here it's 2 hydrogens, 1 oxygen. They are, if I were to write this another way, I would write it like this. Here. And I don't really care what angle you write it at, but I'd write these dashes because I'm trying to tell you those are covalent bonds. You might see it sometimes written like this. All right, fine, same thing. We don't care in this class. In biology, we don't care what angle it's at, but it's water. This is a molecule of water. They are covalent bonds. They're sharing electrons, but these are polar covalent bonds. They're not sharing equally. When you share, it's supposed to be the electron goes around hydrogen, then oxygen, then hydrogen, and it's going like that. I take it one time, you take it one time. I take it one time, you take it one time. This is different. For some reason, especially for us, we always find it here when oxygen deals with hydrogen. Oxygen's hogging the electrons. So hydrogen takes its electron, and then hydrogen gives it to oxygen to borrow. Oxygen takes it around again, takes it around again, keeps taking it. Then maybe one time give it back to hydrogen, and then take it back again. So the same thing here. This oxygen should be sharing electrons with these two equally. There should be like these circle 8 things, right? But it's not. It's looking like this. So unequal sharing. Oxygen is selfish. It's still sharing though. Right? It's still sharing even though oxygen's got it all the time. Hydrogen has it sometimes, once in a while. It's still sharing. It's just not a very nice arrangement. Oxygen doesn't do that with anyone else. When it shares with carbon, it's equal. When it shares with nitrogen, it's equal. When it shares with another oxygen, equal. Just some reason, well, again, because hydrogen's a punk. Hydrogen is either getting its electrons stolen or it's allowing oxygen to take advantage of it by hogging the electrons. I don't know what it means exactly, but one of my sons thinks that hydrogen's a sin. Whatever that is. Yeah, so there's an effect. Whenever you go to check on hydrogen, it doesn't have its electron. Most of the time, it doesn't have its electron. Did oxygen steal it? No. It's just borrowing it like all the time. So there is a positive, sort of a positive charge with the hydrogen. It's not an ion. Oxygen didn't steal it. It still has it, but it's hardly ever in possession of it. So there's like a positive pull, a partial positive. It's not a full-on positive and negative type of deal. It's a partial positive with the hydrogen end. And then the oxygen, since it's always got this electron, well, not always, but like often, it's got like a negative, and that's what this is a D, like a Greek letter D, delta. It's like a negative pull. So we call it like a partial charge, or kind of like a pull, like an attraction. And same thing here with these two. It's doing the same thing, right? So there's like a partial charge here, like a little pull, and a partial negative pull on the other end. And so these are polar covalent bonds. And simply put, they're not sharing their electrons equally. They're still sharing, just not equally. That's a polar covalent bond. You're pretty much only going to see it here with oxygen and hydrogen. That's a polar covalent bond. And that's going to lead us to another type of bond. But let's look at water first. Well, let me see. There we go. This next slide is going to explain it. Why does it always go back to the first slide? Oh, I don't have the slide. Oh, I know what's that. I've got a slide that I'm showing the people that are streaming in, and I'm trying to match it with you guys. So this is what I'm showing them. Even though they can see it, they can see me also writing on the board, so they've got it like twice up there. But I think sometimes one of these things projects backwards. So anyway, let's look at this one. This is a water molecule, right? This is oxygen, that's hydrogen, that's another hydrogen. They're not sharing equally. So we got a little bit of a positive, a partial charge here, a little bit of a partial charge here, a little bit of a negative charge here. Do you already see where I'm going with this? Well, where that's going. This is one water molecule. There's another. So partial positive, partial negative. They're attracted to each other. We call that, and those dots are like shorthand for a hydrogen bond. These dashes are shorthand for covalent bond. But it's polar. And you're like, well, how am I going to know it's polar or like not polar, non-polar? How am I going to know? If it's oxygen and hydrogen, it's going to be polar. That's all. Everything else that you would see, it's not polar. Just oxygen and hydrogen. So this hydrogen bond is a partial positive attracted to a partial negative. It's kind of like an ionic bond. Think of an ionic bond as like two magnets and they're sticking together and like they're attached, right? And so whatever I'm doing with one of the pens, the other one's like following me, right? But this water is attracted, is kind of like, so imagine they're like magnets kind of magnetized, but they're not touching. So when I pull this one's going to kind of follow it. But if I were to just like jerk this away, it'll come off. Like it's not strong. If I take this water like right here and I start to like tug it slowly, the rest of them is going to follow. But if I just take it and pull it off, this is going to come right off. So it's kind of like an attraction. It's like a partial magnet, like a really weak magnet or something, but it's not touching. You know, like when you put magnets together, it kind of pushes the other one. Really don't know how to explain it better than that. But it's a weak bond. It's weaker than ionic bond. So these things break. In fact, when you look at like water, like a glass of water, like liquid water, this is kind of what it looks like. These are all, well, first of all, this is water. This is all a covalent bond. Even though it's polar covalent, it's still stronger than this, right? So this is a water. So they're all, it kind of looks like this. It's all these individual water molecules that are being held together. And that's like liquid water. As soon as you start to heat this up, you're not going to break these bonds. Even though they're not sharing equally, they're still sharing. So you're not going to break this apart when you heat up water. You're breaking all these apart. So this goes its own way, that goes its own way. They're not together anymore, right? That's like steam. So water vapor, when you heat up water, you're breaking hydrogen bonds because they're weak. There's lots of things that can break hydrogen bonds, like heat, for example. Something's like an acid. Acids will break these hydrogen bonds. Your body forms, it's not just water that forms hydrogen bonds, like other things in your body use these bonds. So we've got like 3 bonds. Covalent, based on sharing, that's the strongest. Polar covalent, not as strong, but it's still covalent. Double covalent, stronger, right? Because that's 2 electrons they're sharing. So covalent bonds are like the strongest ones. Then after that, like the less strong, ionic bonds. Then the least strongest, hydrogen bonds. Because it's just kind of an attraction. Like they're not even like touching each other. It's just they're attracted to each other. Positive and then partial positive, partial negative are sort of attracted. So a hydrogen bond, to give it like some kind of definition, a partial positive is attracted to a partial negative. That's what I was kind of talking. Well, no, that's not what I was talking about. But that's kind of what it looks like. Oh yeah, I guess I get where it's going. All right. The tree got me thinking of something. That's why I stopped it there. Forget about this side. stop. Think that I'd be like used to it by now, like how to work it. Not. I think it's that age. When we got away from this, when I first worked here, I was using that. When I was at University of Rhode Island, we were using slide projectors. I don't know if you ever even saw one. I had all these slides like in a book, and I had to like put them in the right order in the projector. And then in class, I'd push the button, and it would go to the next one. And those were on their way out, and people were using these things, right? So, and then I put the slide. I never got the slides the right way, and so I'd have to like click around. I'm like, hold on. I have to like click to the next one, click to the next one. I'd be like, wait. And I have to move back. And then the acetates, I used that up until 2004. And I would just use this thing and draw on the, and I'd have like a stack of them ready, right? And then sometimes it'd fall off the desk and they just like all scatter. And I'm like, oh, I'm just gonna write on the board. But I was quick to use PowerPoints, but like now, using just your computer is kind of old. I should be going to this, and I should be recording this and just dropping this thing online. And I should be using like these pens and writing on it and switching back and forth between the internet and embedding videos in it. And I haven't caught up. But you know what? I don't think anyone else has either. That's all that matters. So, since we're talking about water. So let's talk about water. It's got some things, like when you talk about all the liquids that are around, water is not the only liquid. Alcohol is a liquid, right? So when we compare water to alcohol, for example, it's got some unique properties, right? And one is that water is cohesive, meaning that it tends to stick. Oh, did it again. Oh, did it again. Remember how I got through it last time? It's not pausing. All right. Water is cohesive. Really what I should do is go into the PowerPoint and write the stuff on here. So I don't have to write on the board. Which I eventually will do. It's just with atoms. I don't know, for some reason I gotta like write them out and like make them interact. It's cohesive, it sticks together. I was telling you, like when I pull one water molecule, the other ones come. If you ever like spill something and you take like a paper towel and you see like the water goes up into the paper towel, you don't actually have to put it over the whole thing of water. You could just put the corner of the paper towel up to the beginning of the water will all go into the paper towel. And once the beginning water goes in, the rest of the spill, as long as it's all connected, the rest of the water in the spill will follow it, right? So it's cohesive, it stays together. And that's kind of like this with the tree. That's why this tree's here. So water, like in trees, obviously it comes from the roots. It doesn't come from like the rain and go into the leaves. It's not coming from on the top, it's coming from underneath. Okay, but that's the roots. How do we get the water to like this part and this part? What's happening is that it's evaporating. So some water molecules are evaporating from the leaves, and like that's attached to another one, which is attached to another one. These W's like signify water, right? And it just keeps going down to the trunk. You get what I'm saying? It's like a chain. When that one evaporates from the leaf and goes into the air, it's pulling. The other ones are following it, and it's pulling it all the way down to the roots. and then it's pulling water into it. So call that like transpiration. Some trees like they move a lot of water. Like a cypress tree could move like 250 gallons a day, like from the ground, because it's evaporating from the leaves, and then it's just, the water's just following like a train, right? And it's just pulling it up from the ground. So that's how water gets, and that's because water is cohesive. Like other liquids wouldn't necessarily do that. This is like the part that it moves through. It's called xylem. Hold on, I'll let somebody in. What time do you guys have? 10? Oh, we should take a break. Don't you guys want to take a break? Of course you do. You're zoning out. Let's take 5 or 10 minutes. Hey guys, let's take 5 or 10 minutes. Is that okay? All right. I'm going to, should I stop recording or just keep going? I'm going to stop recording and then, but we'll still all be on here. I'll start recording when I get back. So we're still here.